Hello everyone, and welcome to the third lecture in week 11 in the Intro to Robotics course, where we are going to continue looking at probabilistic robotics. Right? So we have looked at various estimation problems and various kinds of models so far. So in the last lecture, we were talking about how the motion model has to be corrected in the presence of a map, right? So where does this map come from, right? So you can assume that the map is given to you a priori, but quite often being able to estimate the map, right, of the environment in which you are operating in is one of the really an ability that we want an autonomous robot to have, right? So one way of thinking about it is it's a core competency for autonomous systems, being able to detect, estimate the map of the region in which they are operating, right? So formally, what we are going to assume is a map M is essentially just a list of objects in the environment along with their properties, right? You could say, okay, there is an obstacle here, it's in location X, Y, and then the orientation of theta 1, right? So that could be M1, right? So I'm going to look at this as a collection of objects along with their properties. In some sense, this whole map estimation problem is a lot more difficult than what we have looked at so far. All the problems in terms of state estimation and even estimating the motion models and so on and so forth are slightly easier, because even if you're operating in a continuous space, right? So we are at any point of time keeping track of only one location when we are looking at state estimation, right? So all the Bayesian filter problems and all those are slightly simpler. But in the case of mapping, we are literally looking at so many different locations, right? In fact, if you're operating in a continuous space, then you are really looking at being able to represent this continuous workspace in some kind of an abstract form, right? So, so to make the job easier, right? So think of this as a more of a discrete estimation problems. We move it down into this kind of a list of objects and their properties, right? And so the mapping is done in two ways, right? So typically, so this list of objects that we talked about, right? They could either be some kind of a feature-based map, right? So in a feature-based map, N is some kind of a feature index, right? So features could be the different objects in the environment, could be positions of walls and partitions and so on and so forth, right? And so the value of Mn, remember M is just Mn is an nth object, right? Contains other than the properties of the feature, right? It also contains the Cartesian location of the features in the workspace, right? So you can just say, okay, here the XY location, I have a feature. It's like it could be a table. So in which case I would have some kind of dimensions of the table and so on and so forth, right? So the feature-based maps specify the shape of the environment at specific locations, right? Namely the locations of these objects that you have on the map, right? It doesn't necessarily give you a complete description of the shape of the environment where there are no objects, right? So sometimes it's actually useful to have these feature-based maps when I'm trying to do localization in the world, right? So if I'm actually next to a specific feature, right? If I'm next to, for example, if I'm next to a particular building when I'm trying to do navigation, right? It's easier for me to know where I am. Oh, I am next to that building. So that way I get more information when I have this kind of feature-based representation, right? And likewise, another advantage with feature-based representation is it's easy to add additional features, and also it's easy to move an object around, right? So I can adjust the position of an object on the map just by doing additional sensing or getting closer to the object, and therefore being able to refine my position estimate of the object and so on and so forth. So feature-based maps are easier to update in some sense, and I can do this without having to worry about actually verifying any of the other locations or other objects that are there in my map, right? So I can just independently adjust the position of the new features. So that way it's convenient in certain conditions, but in other ways, when I want to figure out if a particular location is free for me to move into, right? Suppose do I have an obstacle or not, like we were talking about in the motion model, right? In such a case, I would really have to run through all my objects, right? All my features to figure out if there is a feature that intersects with that location that I want to move to, right? In such cases, it's easier for us to maintain what are called location-based maps. Like in feature-based map, each mi, right, corresponds to a specific object or a specific feature that I want to map, right? In the location-based maps, each mi corresponds to a specific location, right? So we call these location-based maps as volumetric maps, in the sense that they offer a label for any location in the world, right? So in the feature-based maps, you don't get that. In volumetric maps, they not only contain information about the actual objects, they also contain information about absence of objects, for example, free space, right? So if I want to know if there is a particular location to which I can move to, having a location-based map and seeing that location as marked as free space is a useful thing to have, right? So in many cases, when I want to do these kinds of planning, right, path planning and so on and so forth, I would like to have this kind of location-based maps, right? When I want to do localization and I want to figure out where I am in the map, right, with respect to landmarks and so on and so forth, feature-based maps are easy. And when I want to do planning and I want to do some kind of prediction in terms of where I will end up with, right, location-based maps are more useful, right? And quite often in many practical scenarios, we would like to go back and forth between the two, right? And so for the rest of the lecture, I will look at a specific kind of location map, right, location-based map, which is very popular, which are called occupancy maps, right, occupancy grids or occupancy maps, right? And basically the idea here is they assign to each xy coordinate, right, a binary occupancy value. It's either 0 or 1. 0 means there is its location is free, 1 means the location is occupied, right? That's why it's called occupancy maps. So 1 means the location is occupied. So I can query any location in a world and then figure out whether that location has an object or does not have an object. Okay, so if you can even store it as a bitmap as 0 and 1, and therefore sometimes even for large spaces you can have a compact occupancy grid or occupancy map. So when you are operating in a continuous space, right, so we typically don't look at each continuous xy coordinate value for occupancy maps. What we do is we actually make a grid space, right, or around it, right? So we make like a grid line. So you'll see it later in one of the slides. And for each cell in the grid, we assign a occupancy value, as opposed to assigning it for each xy coordinate. Because if we are operating in a continuous space, then this is not really a practical approach, right? So what we do is we discretize the state space and make it into a grid, and that is when occupancy maps are also called occupancy grids, right? So looking at the occupancy grid algorithm, so in some sense, the goal is to compute the following posterior, right? So given a sequence of observations and a sequence of states, right? In each state, I'm making some kind of an observation, right? I would like to estimate a map M. What is the probability over the map M, right? So remember, M is actually a collection of MIs, right? So for each MI denotes a particular index in the map, right? So it's a collection of these objects. So in the occupancy grid, each MI is going to correspond to a location, right? So the controls really play no role in the occupancy grid maps, right? Since we already know where we are, right? So for each location I make a measurement, I really need to know whether it's occupied or not occupied, right? So I don't really need to know what is the control that will get me through that space. Right? So in some sense, I can assume that the path that I'm actually following for doing this mapping is already known to me, right? So we're going to say that each MI, right, denotes a grid cell with index I. Right, so which is so I'm going to say M1 means index 1, right? So, and an occupancy grid map is essentially just a collection of many of these grid cells MI, right? So for all the grid cells MI, and each MI is going to have either a 1 or a 0. So MI equal to 1 means that it is occupied, 0 means free, right? And I'm going to use the probability of MI to refer to the probability that MI is equal to 1. That it's actually occupied. So whenever you see, whenever we write P of MI, it actually means the probability that the ith cell is occupied, right? So and then what we do here is, instead of looking at this probability of M given Z1 to ZT, I'm going to just say that, okay, what is the probability of MI given Z1 z1 to t and x1 to t, and then look at this for each one of these cells independently. So I'm going to assume that the probability that a cell is occupied does not influence or gets influenced by any of the other cells in the state space, right? It's influenced only by the measurements I'm making and the actual state values, right? It's influenced only by z1 to t and x1 to t. So this makes my problem much easier. Otherwise, I'll have to look at this very large joint estimation problem, right? So instead of that, we'll assume that each cell is estimated independently, right? Now, if you think about it, so where are we getting here? So I have a single variable, right, that I am trying to estimate, right? And this single variable is static. I'm assuming that the cell is static, it's not changing, right? It's not going to get affected by my actions or my movement because we're talking about the map, right? So the map is either clear there or it is occupied, right? That's a single variable taking on one binary value, 0 or 1, and it doesn't change, right? So we already looked at this, right? So we already looked at the binary base filter with static state earlier, and we already looked at the algorithm, right? So all we really need to do now is to apply that algorithm. So where instead of looking at x, right, instead of looking at the state x given a sequence of observations, right, I'm going to look at what is the value of mi, probability of mi given the sequence of observations and the sequence of states I have seen, right? It's exactly the same algorithm. So instead of looking at it as a state estimation algorithm, I'm going to run the binary base filter with static state algorithm to solve the occupancy grid mapping problem, right? Using the same kind of log odds representation of occupancy, right? So this algorithm should look very familiar to you. You can go back and look at the binary base filter with static state algorithm. And here for each, so what do I have here? So I have the likelihood of the occupancy that I have seen so far, right? Starting from the beginning. So basically t minus 1 is like my belief state on the map. Okay, it's like the belief state on the map, right? So what is the likelihood that cell I is occupied at time based on the measurements I have made till time t minus 1. So that is what this set is, right? So you'll have one entry for each value for I, and then you have your current state and your current measurement. Okay. Now for all cells mi, right? Now if mi is in the perceptual field of zt, so what do I mean by that? That means that when in xt I'm making a measurement zt, right? So how much of the world can I see at zt? Right? Depending on what kind of sensing do I have, it's not that I'm only looking at the current state I'm in, right? So I could look at a region of state around it, as we'll see in the next couple of slides, right? So for example, I'll just look at this for the measurement model, right? So even though I'm here in this particular state right now, so I'm actually able to see a lot more states based on my field of vision, right? So I have this field of vision, so I'm able to see a lot more states, and I can actually make estimates about whether these states are also occupied or not just by making a measurement at xt. So when I say I'm at xt and I'm making a measurement zt, that doesn't mean zt returns information only about the current cell occupied by the robot. It could actually give me information about more parts of the state space. So that's basically what we are trying to take into account here. So when I say if mi is in the perceptual field of zt, that means that the measurement zt gives me some information about the cell I, right? Then I update the log likelihood, right, using the inverse sensor model that I have earlier, right? So if you remember this expression, so this is L t minus 1 comma I, which is my old belief in the likelihood form, right? And then the inverse sensor model, so the likelihood through the inverse sensor model, and minus L naught, which is the initial likelihood that I start off with, right? So this is my update equation, right? And if it is outside the perceptual field of zt, that means I can't make any estimate about whether cell I is occupied or not. If it's outside the perceptual field of zt, then I leave the likelihood as it is. So the new belief state is same as the old belief state because I have not made any measurement on cell I for me to change this, right? And I do this for all cells mi. At the end of it, I get the new map, right? This is the new belief over the map. Remember, what we are looking for is a probability of m, right, given x1 to t and z1 to t, and this is the new probability of m given z1 to t, x1 to t. Okay. So I hope that's clear, right? I'm going through this a little faster because we have already seen the binary base filter with static state, and this is exactly the similar kind of an algorithm, right? Except that instead of looking at the belief over your current location, you are looking at the belief over a particular cell in the map, right, in the occupancy grid. Okay. So now the interesting question is, okay, how do I come up with this inverse sensor model to use in this occupancy grid algorithm, right? So how do we come the occupancy grid algorithm, right? So so what we do is as follows, right? So just think about this for a minute, right? So if the robot is here, right, and there is an obstacle either here or here, there are two different situations where we're talking about. In both cases, the robot has the same kind of field of view, right? The robot has like a 15-degree cone of vision, let us say, right? And in one case, because there's an obstacle nearby, the robot is able to look at all these states, all the states marked in white, and it can tell you these are clear, and it can look at all the states marked in black and can tell you there's an obstacle there, and all the gray cells, it can't give you any information over and above what you already know, right? So this is not something that the robot, the current measurement can give you any information on, right? And here is a case where there is an obstacle that's a little farther away, right? The robot could potentially, right? So could potentially look at a lot more states here, right? The robot could potentially look at a lot more states here, right? And then it can give you information about all of these, saying that they are clear, because this is in the field of view, there is nothing that stops it until it hits the obstacle, right? Beyond the obstacle, the robot doesn't know what is there, right? Before the obstacle, the robot knows what are the cells, and these are all free, and anything outside of this field of view or behind the obstacle, it can't give you any additional information, right? So the inverse model is basically implemented in the log odds form directly, so that I can just use the inverse model here instead of saying the log odds of the inverse model, right? So that's what we had earlier. This is the log odds of the inverse model. So instead of saying that, I could sorry, you have to cancel that. Okay. So instead of saying the log odds of the inverse model, I can just say the inverse model here and learn the inverse model in terms of the log odds. Okay, and so here you can see that everything that is white means it is free, everything black means it's occupied, everything gray means I don't know really. Okay, so how do we go about doing this? And right, so here is an algorithm that tells you what is being computed in the previous slide, right? So I'm going to assume that the current state xt is given by x, y and theta, right? So x, y and theta, and the cell I, right, the index I denotes a cell mi, and which is centered at xi, yi. So if you think of this as a cell, right, so the center of the cell is what I denote as xi, yi, right? Now r is the distance of the cell from the robot, right, and phi is the angle the cell subtends with the robot, the direction the robot is facing, right? So phi is the angle it subtends with the direction the robot is facing. So now among all the possible sensors that could be looking in that direction, remember zt is a collection of all sensor readings, I picked the one that is pointed most in the direction of the object, right? So this means that, so this is the sensor, theta j sense is the sensor that is pointed as close to the direction of the object from the robot, right? So I picked that. Now what I do is, if this object, right, is farther away than the maximum range of the sensor, or where the sensor says there is an obstacle, right? If the object is farther away than the maximum range of the sensor, or where the sensor says there's an obstacle, whichever is the minimum of the two, right? Then I say that, hey, I don't know anything, so I'm going to return L0, right? Or if the object is too far away from the direction the sensor is looking. Remember, this is the sensor that is the closest to the object, that's looking in the direction closest to the object, but even then the object is too far away. In both these cases, I am going to say that I don't know where it is. So both these cases correspond to, so the first condition, right, the R condition corresponds to the cell being in one of these locations, right? And the second condition, the one on the phi, corresponds to the cell being in one of these locations, right? So in both cases, we say that we'll return L0. So what does it mean to return L0? Remember, if you plug in L0 here, so I'll have L0 and this will become minus L0, so they'll cancel out. So I'll basically leave the belief as it is without changing anything. So that's what I mean by saying I'll return L0 there, okay? Then if ZTK, which is the distance of the obstacle, right? ZTK is less than Z max. That means that the robot has sensed an obstacle, right? And R minus Z max is less than alpha by 2. That means the distance to the cell Mi, right? The distance to the cell Mi is within the object, alpha is the object thickness, right? So it's within the object thickness from the maximum range, right? So in which case I'll return that the cell I is occupied, right? Or on the other hand, if the distance is actually less than, R is the distance to the cell, right? If the distance is actually less than ZTK, which means this ZTK is the distance at which I have sensed an obstacle, right? If R is less than ZTK, then I'll say R is free, right? Then I'll say the cell Mi is free, right? So L free, right? So the cell Mi is free if R is less than ZTK, right? But if R is not less than ZTK, right? If R is actually greater than ZTK, then I'm going to say it's alpha by 2. Then I'm going to say that the cell is occupied, right? So what do I mean by cell is occupied, right? And so this is a algorithm taken from the book, and there's an error in the book itself. So here in this case, you should read that as, so that means I have detected an obstacle that is within the maximum distance of within the maximum range of the sensor, right? And the distance of the cell is within the obstacle thickness of this distance, right? In which case I would say that it is occupied, right? So this should be ZTK. Or if it is less than ZTK, right, then I'm going to say it is free. Okay, so that's basically the algorithm. Okay, so this is how I build up an inverse range map. So I've talked about two kinds of maps. One which is a feature based map, which is typically more useful when I want to do localization, as we'll see a little later. And the other is this kind of location based map, of which the most popular is the occupancy grid map. And we just saw that how we can use the binary Bayes filter with static state and an inverse sensor model in order to estimate the occupancy grid map.